I have no right answer here. I just wanted to give some insight into some of the things that he's talking about, that he's sending a message, in my mind, on like how they kind of do generic programming, and the things they kind of avoid is, it sounds like, minimize compile time overhead from templates, but still use them a little bit. Don't use multiple inheritance, because just in general, that's kind of like not smart. And then minimize the runtime type information overhead, which are things like dynamic cast, right? And the reason why is you have a performance penalty, which basically indicates to me that don't use templates that much for generics, don't use subtype uh, polymorphism for generics because they're the RTTI. So use void pointers. Okay. This is probably where I'll end part one, and then we'll continue.
Runtime type information, that's off the table. We definitely don't use STL, to go back to the question of templates and compile times, but also because we found, generally speaking, it's not that we have a replacement for STL that we think is somehow magically better, it's that it doesn't actually solve the problems that we want to solve, and we want to solve the problems we have. Custom allocators in the same way. We don't have the sort of general dynamic, we don't use the general dynamic heap management. We allocate all the memory up front. We divide it into sort of a set of hierarchies, then each sort of sandbox manages the data own way that's appropriate to its system. So we have tons of custom allocators that will work inside those sandboxes. Some of them maybe that sort of familiar kind of heap management inside of a sandbox block. Some may be small block allocators. Some may be sort of linear allocators for systems that just need to sort of linear burn through and then reset. We have tons and tons of different things. Custom debugging tools, again, back to debuggability. We have a lot of tools that sort of introspect into our data and look, either pull it over to the development PC from the console so that we can examine it. We have tools that do examination live. We have tools that do examination offline and sort of dump a bunch of data so that we can analyze it. Tons and tons of debugging tools. So in a lot of ways, because the Mars rover project is sort of a very small embedded system with very limited resources, and certainly a console at the scope of PS4 or Xbox One is much, much bigger by comparison. They share a lot of similar properties, right? They are these sort of fixed resources, and you want to take advantage of those resources. So in that way, we end up at a lot of the same places. So back to the title, this data-oriented thing. What does it mean? Is it even a thing? Is it like is it a process? What does it mean? So I want to talk, when I say it, I want to talk a little bit about what I mean. And fundamentally, this is something that it's just a fact, right? It's not a belief. The purpose of all programs and all parts of those programs is to transform data from one form to another. Physical fact, that's the point. But this is sort of the reminding.
Maybe. So I have a lot to say about this, but just first I want to start with potentially agreeing with him. In classical program synthesis, the input-output pairs that we're actually just publishing a paper about this. Input-output pairs are essentially the input that you give a program and the output that's expected. And this essentially functions as the specification of the program. This is how traditional program synthesis sort of works. So you have input, and then you have a program, which you're going to try to find, and then you have output. Okay. Which is what he's saying. Or at least that's the way I think about it. So in that sense, I don't think that he's wrong. However, I think that there's more to this. And the part that I think there's more is that there is also state. And that is more than, I think, just the output. So, for example, if you, yeah, a very simple example is, let's say you have a language model system that's going to do what he's saying. So, the language model, it's a program. It takes input to the LM, and then it generates output, and it's doing what he just described. All programs and all parts of those programs is to transform data from one form to another. There you go. Cool. So it just proves his point. Okay. But what about this? What about the case where you have a language model, input, output, but it also does continuous learning? So it has input, just like this other guy. And then it has the language model that uses some degree of reinforcement learning. And then it has this output. And in addition to that, it has a state change. And that state change is internalized into the system, and the system evolves. Is that captured in this? I don't know. Maybe. Possibly. But that's why I would say that's why I paused, is I think he's mostly right. And I think in the traditional sense of program synthesis, he is right. But I think that there are new software systems that are evolving that fundamentally disrupt classical software systems that we've built, where this paradigm is no longer sufficient. That continuously evolving software systems is an emerging trend with reinforcement learning and other continuously learned AI systems. Even Merle stuff does this. Like, our models self-improve. So they will take input on code, and then they will output something. We have a little button that we can click on, and then it will use the things that it's looking at as a reinforcement signal, and it'll level itself up. This is an additional thing that classical software systems, I think, did not do. I don't really think, but the future, I think, is. So when you start to consider the power of AI and what I refer to as the self-star stuff. Self-star. What does the star stand for? Stands for things like this. It's doing introspection. It's doing debugging. It's doing optimization. It's doing feature completion. It's just doing stuff. This self-star stuff is, I think, deeply aligned with the machine programming movement. And so I want to be super clear. This talk was 11 years ago. I'm not picking on Mike for not being a fortune teller and seeing the future. So this probably made a ton of sense in 2014. But now in 2025, there's new stuff that's going on. And with that new stuff, I think this is, by the way, this is brilliant. This is very good. But I think it can be leveled up just slightly with this state observation. And I don't think that that has anything to do with the input and output. I think it's a third dimension of analysis. And the truth is, I think this is more what programs are going to do moving forward. And there's going to be more. Like I said at the beginning, I'm not the knower of all things, but I already see this pattern emerging, and we're already doing this, and this is something that's new. I used to not do this. I used to think, whoa, wouldn't it be cool if we could do this? We do this now. It happens all the time. Okay, back to you, Mike.
Principle of why we're doing what we're doing. And to that end, if you don't understand the data that you're transforming, right, you don't understand the problem at all. Conversely,
yeah, I totally disagree with this. I absolutely disagree. 100% I disagree. And I'll give you an example. Is I have a photo of a dog, and I want to have this be labeled dog. I understand the data, and I understand the thing, but I don't know how to build this thingamabob. So, sorry, let me rephrase that. He's saying if you don't understand the data, what did he say? Sorry, we have to roll back just a second. Don't we? Did I miss? If you don't understand the data, you don't understand the problem. Okay, yeah. So let me rephrase this. We have the photo of the dog, so I do understand this data, right? A little bit, and then I know what the goal is. But here's the thing: is I don't deeply understand the data enough to where I can create the solution, and because of that, I'll use an AI to do it. And this is where I think one of the reasons why AI comes in. Yeah. Again, this is okay. This probably made a ton of sense in 2014. In 2025, with AI, I have a different view. So I'm not picking on Mike. Immediately this is like no, I don't think this makes sense, because we build AI systems now to help us understand the data. So we understand the problem, but we don't understand the data, not exactly. And that's what the AI system helps with. Now, is that good? Is that bad? I don't know, but I see systems being built this way. So I take it back. I don't know now. At first I said I totally disagree. Now I'm not entirely sure. I need to think about it, but I'm going to leave this in because I want people to see how I'm trying to evolve my thinking in real time. So maybe Mike is right. I'm going to think about this some more.
and if you don't understand the data that you're transforming, right, you don't understand the problem at all. Conversely, you understand a problem better by understanding the data that you're working with. And different problems, this should be obvious, require different solutions, right? Everybody should agree with that.
Agreed.
So if you have different data, you have a different problem, right? Which require a different solution. If you don't understand the cost of solving the problem, you don't understand the problem, right? If you can't reason about the cost of the things you're doing, you don't really understand the problem. If you don't understand the hardware, you can't reason about the cost of understanding the problem. Every piece of hardware, every imagined
1,000% agree with this, Mike. And this is actually, just to be clear, this is why a lot of the AI companies today, I think, are cooked. Is they understand, this is, again, if we talk about machine programming, the 4 domains: ML, software engineering, PL, systems. Systems is hardware. And there are a bunch of well-intentioned folks that are building AI systems that they know how to download things from Hugging Face and wherever, but they don't really understand some of these other things, and they definitely don't understand the hardware, so they don't really understand the cost of what they're building, which is part of the reason why I think a lot of people are doing language model things, because they don't actually understand the economics of it. You need someone that is deeply well-versed in machine learning as well as deeply well-versed in systems. Simultaneously, it needs to be the same person, because then they can be like, oh, right, that doesn't make sense. Sort of like how I can tell Mike understands systems very well, but he also understands programming languages. How can I tell this? His comment about RTTI, he's like, oh, we don't do this. Why? Because there's overhead in runtime type information. And he knows that because he understands PL deeply, but he also understands hardware deeply. So this is the point that I'm trying to make is to build video games, you have to generally understand the three things: software engineering, PL, and systems. But to build machine programming systems, there's now a fourth thing, which is machine learning. Unfortunately, a lot of the world is like, ooh, shiny new thing. And so their thinking cap comes off and they, well-intentioned folks, but might be missing the mark a little bit.
Imaginary set of hardware that you're going to be working with is finite and has some range of performance characteristics. And that's the only way to consider how you're going to solve it is to consider those characteristics. And everything universally is a data problem, including usability, maintenance, debuggability, et cetera. Everything is a data problem. It's not a code problem. And solving problems you probably don't have creates more problems you definitely do.
Okay. When you are engineering systems, you're an engineer, you're a developer. I think this probably makes sense. When you are a scientist and you are inventing new things that don't exist, I don't think that this stands. And the reason why I don't think it stands is a lot of those scientific breakthroughs, they have far more to do with understanding the thing that they're inventing. The data is critical, but it's the part where he said, like, it's the data that matters, it's not the code. You don't, the way the scientific method works is you generally don't just take the data and then invent a thing that conveniently matches this thing that you don't understand. Instead, you will look at the data and you'll observe, and then you will have a hypothesis, an aha moment. In this sense, this would be the code. That is principally important for scientific advances. And so when you're thinking about research engineering, not product engineering, I don't think this stands. But I want to also be fair. He's not talking about research. He's talking about building video games. And so I think that in that context, he's right. And this is part of the reason why I wanted to do this React video is most of the things that I think Mike is saying are totally on point. I think that one of the things that I would do to potentially just level this up just a little bit is just add the disclaimer of like, so these are largely fixed to this domain. And so from this lens, right? From this lens, this is what I believe. What's interesting is that now that he's leveled up to this data-oriented design principle, which is a broader category than just video games, right? I quite like, by the way, I quite like this. I think he's onto something really interesting here. But because his focus might have been a little bit too narrow in just the domain of video games, he might be missing some pieces that are now going to be touched on because people like me that are really interested in these big ideas like data-oriented design principles are going to be attracted to it and think, oh, this is actually super cool. And then I'm like, whoa, no, my problem is slightly different. And so he's over. In one hand, he's very general, but then in another hand, I think he's probably a little too constrained. And I think that at least for me, it's causing a little bit of confusion and taking me a moment to kind of sort it out in my head. Yeah.
So avoid adding problems to the space that you don't have, and you know what problems you have because you have analyzed the data. And latency and throughput are only the same in sequential systems. And just some rules of thumb. Where there's one, there are many. So, as a rule of thumb, you look in the time axis if you can, and you solve the most common problem first, which is, I have a bunch of these things that are definitely going to happen over time. That's the most common issue. That's the one I should manage, as opposed to trying to imagine that, this one thing exists in a vacuum. Rule of thumb, the more context you have, the better you can make the solution. So don't throw away data or constraints that you need. You want to know more about where something is going to be used, how it's going to be used, what data is acceptable, what ranges are acceptable in order to make an appropriate solution.
1,000%, yes.
And I think fundamentally for us, this sort of concept, this non-uniform memory access, access concept extends over time for us as well. Where it's not just on the console, but the data that's on the console also, we conceptually view it as extends to, the hard disk of which would be read and the Blu-ray, which will have served that, and then back to the development PC. That data got built from a source data, which was then built from, Maya or whatever, or our development tools, all the way back to the original artist with the mouse, right, or keyboard. So there is this sort of stream of input over time, and we have to manage that entire pipeline and understand the cost of data access throughout that entire pipeline over time, not just this sort of, we don't look at it in a vacuum and sort of this individual access at this one point in time.
Okay.
And most importantly, I think, software does not run in a magic fairy ether powered by the fevered dreams of CS PhDs.
So, brother, preaching to the choir here. I have, because I have one of those things, I think I probably know a lot of these folks, and I love many of them. They're great, but sometimes, what's the saying? In theory, there's no difference from theory and practice, but in practice there is. One of the things that I don't love sometimes is when some of the hardcore PhDs have a disconnect from the world of reality. They lose their ability to think about things pragmatically rather than just from a theoretical view. And yeah, Mike, I'm with you, man.
Software's real engineering that runs on real hardware to solve a real problem. And ultimately, reason must prevail. Like if what we're doing is unreasonable for any reason or imaginary, then it has to go. So that hopefully gives you some context of what I mean when I say data-oriented. So is it a thing? Well, it's certainly not. These are not new ideas, right? There's nothing in here that's new or news. It's really just a reminder for me, for others, of sort of those first principles. And reminding us what's most important, concentrate on that, get rid of everything else. But to a large degree, the only reason we're talking about this, the only reason I've ever talked about this, is because it has been a response to the broader culture that C++ has engendered. And most prevalently is what I call the three big lies. And those are lie one, that software is a platform in and of itself. Lie two, that code should be designed around a model of the world, just your mental model of the world. And third lie is that code is more important than data. So, lie number one, software is...
Just to be clear, so I think I agree with him. I also have a very different take. Code is data, as far as I'm concerned. I mean, that's how I build the systems that I'm building, is we reason about code as data. So I agree with him that data is super important and code is data. So there's no distinction, actually, in my mind. I think I'm actually in violent agreement with him, probably on all three of these.
Platform. This should be super, super obvious, right? Hardware is the platform, right? You have text, you have data, goes into some CPU, spits out other data. Like that's the point. Different hardware, different solutions. You have a different set of hardware. The solution is by necessity going to be different.
Yes.
If I'm programming for a 6502
Yes.
versus a cell.
Yes. This is exactly what I'm saying about how it's the difference between large language models and small language models. It's totally different because the hardware is the platform. Small language models require significantly fewer resources, and that is a fundamentally different problem that you're solving than a large language model. So I violent agreement with him. He literally now he's living in the future because 11 years later, this argument that he's making is probably more profoundly important in my mind today than it maybe even was back then, because this is the big split that I see in the future is the lies that are being told is software is that platform. And so with language models require all this cloud infrastructure. No, they don't. They do not, right? Large language models do, and that's a software problem, but the platform is actually the hardware. So if you have a single commodity processor, then you can build a language model that runs on it. It's a small language model. And that's actually Tim Matson and I, one of those actual PhD people, we're working on using that as the working definition of small language models. So 1,000% agree, Mike. Yes. Hallelujah, brother.
Versus the ATI 5870 versus some ARM versus some a server farm full of processors, right? x64 processors. These solutions in each case are going to be entirely different.
Yes.
Because they're
yes.
Platforms. They have different constraints, different physical constraints apply. You cannot make a solution independent of the actual platform or finite set of platforms that you're working for.
You cannot. Yes.
So reality is not hacked, right? It's not something you're forced to deal with to solve your abstract theoretical problem.
Yeah.
Reality is the actual problem that you're trying to solve, right?
Love it.
It doesn't make your code less nice that you had to actually do something with actual data on a real actual platform to make it actually work. Like that's the point. That's the thing it should do. So if you think the right way is some way other than the way that actually works in context, then your idea of the right way is wrong. Code does.
Yes, Mike. Yes, and the truth is, I think I kind of know why he's getting so fired up about this, because some of the people, they will get adamant about this, like just working in this abstract space because it's more general and all this stuff. And then again, back in the world of reality where we actually have to solve real problems, we don't have this luxury. So that's not helpful. Yeah, he's on a roll now.
It should be designed around model of the world. This one sort of has trickled into the C++ culture from that sort of object-oriented space, right? And sort of building up that model of the world and trying to codify that in that process, hiding data is implicit, right? That's sort of what most people would even suggest is the point of it. But this is bad. It confuses two things, two important things. One is the main.
No. I don't think I agree with this. And an example of this is something like federated learning. Federated learning hides the data. It depends on the domain that you're working in. There are certain spaces where you cannot have the general public kind of know the data, otherwise bad things happen. So in healthcare, right, the Hippocratic Oath. So you need sort of a federated learning system that hides the data, but it can still do things from that data. So you can't broadcast this to the whole world, because if people knew, if our social security numbers are all out there, then identity theft is running rampant. So maybe this is not what he's saying, but he did just say hiding data is I think a bad thing. And I don't necessarily agree with that. There are a number of cases where hiding data is, I think, exactly the right thing. And you can still build software systems that function. You just need degrees of abstraction to use things like federated learning. And it's not just restricted to federated learning. When you do degrees of abstraction, you can remove certain amounts of specificity that could otherwise compromise the system. So I think I don't fully agree with this one, or I agree with the high level concept, but I think I disagree with the rabbit hole that he's going down.
Maintenance, which is a good thing. Like, we want to be able to maintain changes to our access to the data. Great. But it confuses that with understanding the properties of the data. What is the data? How does it work? How big is it? What's in there? This is going to be the most important thing that we need to know in order to actually solve problems. And confusing these two things, or confounding these two things, means at the cost, potentially at the cost of slightly better maintenance, we have now made our problems very, very difficult to solve, or at least to solve well.
I'm not sure.
And this whole idea of world modeling implies some relationship to real data or transforms, right? It's as though if I have some model of the world and I codify it like that, that's actually the thing that's happening. But the problem is that in real life, classes of things, right, are fundamentally similar. They really are the same. A chair is a chair in real life. But in terms of data transformations, in terms of what we do, these classes are really only superficially similar. So, in our context, in the context of a game, we have a chair and a physics chair and a static chair and a breakable chair. These things are not at all similar. Like, there's almost nothing that's the same between these contexts, right? How they're handled, how the data is managed, how the data is transformed. There's virtually nothing that is the same here. And yet, the tendency would be, because they share some world modeling similarities, or similarities in the real world, that they ought to be connected somehow in sort of the code hierarchy, which is nonsensical, to be honest. Mm-hmm. So world modeling in general leads to these sort of monolithic, unrelated data structures and transforms, leading to all kinds of other problems that you shouldn't have in the first place. Mm-hmm. So
yeah, I think
from
I
my
agree.
perspective, I think that world modeling is trying to sort of idealize the problem away, sort of back to there is no software ether that we're running in, that we really need to understand the data and the hardware that we're working on. You can't make a problem simpler than it actually is, right? The actual reality is you have this finite set of hardware. The actual reality is you have this finite set of data. You can't make it simpler than that. And I sort of see world modeling as the equivalent of self-help books for programming. It's sort of like trying to engineer by analogy, or engineer by storytelling, as opposed to engineer by engineering. And that makes it, not as good. Lie 3.
Agree.
The code is somehow, for some reason, more important than the data, that we spend so much time focusing on the code. So much time talking about, we're all here, honestly, to talk about the code, right? So much development time and brainpower spent talking about the code.
Just as an aside, I see this in the AI world as well. This is probably the reason why Gutsy David posted this, is I see this with the shiny new toys of the language models, right? And they think, oh, it's just a transformer, and the transformer is going to solve everything. I don't think so. I think that data is fundamentally important, and without making data a first class citizen, you really restrict yourself. And I see lots of people restrict themselves massively because they take this similar view. So in this case, just replace the word code with model. The AI model is more important than the data. No, it's not. The AI model is important for sure, but without the right data, especially high quality, high fidelity data, either high quality in a good sense or high quality in a bad sense, high quality in some dimension, it doesn't matter how good your model is, right? So, yeah, Mike.
When the vast majority of the time, the code is not the real issue. The code is a minor issue in all the things that we work with. It really is the data that we're dealing with is the thing that we are reasoning about, and the thing that's the actual problem. As I said before, only purpose of any code is to transform data, right? It's got to get it from this form into this form. Whether that, at a high level, it's from like data on disk and player input into what's on the screen and the speakers, and that's sort of hierarchically down to the systems and the things that are transforming data inside the system. And the programmer is fundamentally responsible for that data, right? Fundamentally responsible to make sure that transform happens correctly, happens fast, happens in a maintainable way, not the code, right? The code is the tool that we use to do the transformation. So the programmer's job is not to write code. And I think people really, really don't want to believe this. Like, it's not your job. Writing the code is not a job. Writing the code is the tool you use to do your job. Your job is to solve data transformation problems, right? Solving the problem is the job. So to that end, right, only write code that has direct, provable values that transforms the data that you need to transform in a meaningful way. And in order to do that, you have to understand the data so you understand the problem so they can solve it appropriately. Which means that there is no ideal abstract solution to the problem. There is not. You can pretend there is, but there is in fact not.
Yep. And maybe this captures why I think AGI is just sort of nonsense. I think the idea with AGI is there's some abstract representation of the world's knowledge that can be ingested by this generalizable AI model that just somehow functions on every different modality in the universe. And then somehow we get AGI. But then back in reality where Mike and I live, it doesn't work, right? This is nonsensical. And I think that people that are pitching it this way, I don't want to say anything bad about, this isn't about anyone in particular, but it's like they may not know enough to know that it's wrong, or they may know enough to know it's wrong and they're still doing it. It's like those are sort of maybe the two general vectors.
Cannot future-proof. This is just a trap that people fall in. That they could believe this whole idea that I can just make some code and it will last forever across all imaginary systems that could ever happen in the future, right? That's simply not possible. Like, there's going to be some finite range which you have not accounted for. We're not going to take, for instance, an engine that somebody developed for SNES or Atari 2600 and try to put it on the PS4 and develop the same kind of game.
Yeah, I think that what you do here is you essentially, what you take with you are the principles. You take with you the things you learned, right? But you don't take the code, right? The code is an embodiment of an idea that helped you kind of learn something. So you leveled up and you're better now because you got to experience something and you solved a problem. But now as you march forward, the problem is different. And so you don't take this thing with you and try to force it in because you're just trying to like, you're trying to not reinvent the wheel. But the problem is the wheel's different, right? And so, and this one's tricky because certain things I think can carry forward, but other things cannot carry forward. It just depends on the level of maturation in the existing field. Let me give you an example. In my view, the quality of audio as an audio, I'm a massive audiophile, right? I think some of you know. Listen to music all the time. I love it. From an audiophile's perspective, I don't think that the quality of audio has massively improved over the last 10 years. I don't think so. I think that even with the spatial audio or whatever, and Dolby 10.5 or whatever the heck it is today, I don't notice that much of a difference. I got to be honest. It sounds, I think that we reached some sort of nines problem maturation, maybe in the early 2000s or so, and there hasn't been much forward progress. partially because the range of sounds that the human ear can process is limited, right? It's sort of a similar reason with TVs. There's only so much fidelity we can add. We can do 8K and 16K and 32K, whatever TVs, but will anybody notice? Right? Like I notice a little bit of a difference between like 2K and 4K, a little bit. But when it's 2K, I think it's probably still fine. So now I've moved away from audio. Now I'm on to the TV. TV, I think, is reaching its level of maturation, like audio. But keep in mind, audio came first, right? We've been doing. Think about it like we've had songs and stuff. We had the radio before we had the video camera. Okay, so we were playing songs and stuff, and so we were at it earlier. It's easier. We understand radio waves before we could create some other stuff. So it depends on the maturation of the domain. And a good example, I think, now is things like the internet speed. Internet is still like an evolving technology, and it has massively leveled up over the last couple of decades. So we're at the point where we like have fiber now, and we can do hundreds of megabits a download per second, which is somewhat novel, even if you roll the clock back just like 5 years. So roll the clock back 5 years and compare the state of the art for the internet, what you could get versus the state of the art you can get today. Now do the same exercise for the quality of audio. Have they leveled up the same? No. And so that's why maturation in the domain is the key idea in terms of whether or not you will continue to invent new solutions. For domains that have massive amounts of maturation, like kitchen utensils, maybe we're at capacity. There's not much more to do. Seeing glasses, right? Maybe we're at capacity. There's not much more work to do. But in terms of like AI modeling, no, there's a whole bunch more to do. So I think that that's an important contextual piece to consider here.
Games, the problem has fundamentally changed over time. So to recap the lies, lie 1, software is a platform. Lie 2, code should be designed around the model of the world. You cannot future-proof. This is just a trap that people fall in. That they could believe this whole idea that I can just make some code and it will last forever across all imaginary systems that could ever happen in the future, right? That's simply not possible. Like, there's going to be some finite range which you have not accounted for. We're not going to take, for instance, an engine that somebody developed for SNES or Atari 2600 and try to put it on the PS4 and develop the same kind of games. The problem has fundamentally changed over time.
Exactly. And really, again, this has to do with maturation, is that like if we think about maturation of computing technology, given the fact that Dennard scaling stopped in the mid 2000s, you likely could actually start to use some of the models that would exist at that inflection point, because the additional compute that you can get in today's hardware is not much more, right? So I agree with what he's saying. Like, you can't take the Super Nintendo model or the PS2 model and think you can use it for like the PS5 or today's laptops. But I think that the giant leaps forward that you would have from things like the Atari to the Super Nintendo to the PS5, we are reaching the logarithmic cap here prior to a jump to like quantum. Yeah. Ish. And not considering advances in AI for like super intelligence.
Time. So to recap the lies, lie 1, software is a platform. Lie 2, code should be designed around the model of the world. And lie 3, code is more important than the data.
I agree 100% with all of his lies. I think that I'm in strong, I violently agree. Love it, Mike.
So what problems do these lies cause? Generally, the things that you'll see, the things that I certainly see, are poor performance, poor concurrency, poor optimizability, poor stability, poor testability. So we build up all this other infrastructure on top in order to try to solve these problems that we've created for ourselves. So solve for transforming the data that you have, given the constraints of the platform, and nothing else. Be some finite range, which is the model of the world, and like 3, code is more important than the data. So what problems do these lies cause?
Wow. Oh boy. I did not expect it to go this way. But I think Mike just stumbled across something that is really profound. He is talking about this in the context, essentially, if I were to summarize, he's talking about all of these problems in the context of building software and thinking mostly for like video games, right? And he's talking about how these lies are they're going to have these consequences if you believe them. This is actually exactly what is going on with, okay, not exactly, but 99% close to what is going on in the world of AI today. Because people, I think, continue to believe that language models are far more important than data and all of this other stuff, you get extremely poor performance, and people somehow just, that's, yeah, it'll just magically get fixed. How? The concurrency thing, admittedly, I think that was actually one of the big leaps forward with the transformer model, because long short-term memories actually are essentially serial. So that one we can put to the side. Poor optimizability, yeah, I think that that's actually happening. Poor stability, yep. They have massive stability things like with hallucinations. And then testability, yeah, they're stochastic. What the language models are. And therefore, testability, you test it and it's like, oh, it's right. Okay. And then you test it again and it's wrong. So he's knocking this out of the park now. I need to take a quick bio break and we'll keep going. Alrighty. Let's keep going.
Generally, the things that you'll see, the things that I certainly see, are poor performance, poor concurrency, poor optimizability, poor stability, poor testability. So we build up all this other infrastructure on top in order to try to solve these problems that we've created for ourselves. So solve for transforming the data that you have, given the constraints of the platform, and nothing else. Just do that. Let's look at just a simple example to help put this in some context. Dictionary lookup. I have some keys, I have some values, I have sort of a key-value pair, and I want to get the value given a key, right? In the traditional sort of code, if I'm thinking about the code first, this table is what I expect to see in memory, more or less. The key and the value will be associated with each other because in the mental model of the programmer, they are associated together. It's a key-value pair, right? But the problem is, the reality is that they're not actually associated together. The most common operation is, if we hadn't analyzed it, would be the search on the key, right? And if we look at that, what's the statistical chance that we will need value on any given key as we're sort of iterating this list? And it's very low, right? It's only on the one hit that we have. Most of the time, we are not going to need the value. Most of the time, we're going to be iterating through the keys. That's what the data tells us. That's what the problem actually is. And these two things are not actually associated with each other directly. So what happens is that this scales toward the worst case. As you have more keys and more values, it gets less performant per pair. And you end up loading, as you're iterating the keys, you're loading the value, each value into Dcache, and you're immediately throwing it away, right? Because the vast majority of the time you're not using it at all. So you're wasting quite a bit of your bandwidth on your machine. You're doing things that are unnecessary because
Yeah, well, I mean, sort of. I don't think that he's wrong here, but I think that he's making a couple assumptions. The first is that this table is principally for queries or lookups that will do augmentation. It's not for full iteration. And it really depends on the problem that you're in. Sometimes you will have these key value pairs and you will actually do a full iteration on the whole thing every single time. Point in case is the way that machine learning models are trained on training data, that they literally take the whole data set and iterate through the whole thing, epoch over epoch over epoch. And it uses both the input data, which in this case would be like the key, and then the value, which is the output. So it's principally, in my mind, related to the problem that you're solving and essentially the domain that you're in. But in the general case that you have like a dictionary where you're trying to find the definition of something, I think that his point is valid, is that most of the time you're looking for the value on a single key. And as you walk the keys in some capacity, whether it's, and by the way, I'm just trying to be fair here. I'm trying to not tell you a lie or convince you otherwise. I think that even with things like, I think that the STL actually does a separation here for things like maps. So I think that it does actually, we will have separation between the key iterators and then the actual values, which is why when you do, when you get a hit on the map, you have to essentially invoke dot second or something, because I think that it actually will carry it with it. I'll have to double check. Um, but so yes, I think that maybe what he's trying to point out is when you are storing this and you're iterating, you generally want to do iteration using just the keys. Don't carry the values with you because that's just sort of a waste, and it should be optimized for potentially fast iteration on the keys, whatever that means. Probably, I mean, it depends on what you want to do, but it could be contiguous memory that's stored basically like in a vector or something where you minimize cache misses, or minimally if you store it the way that I think C++ does in various things like their sets and their maps. You know, you can do tuples, this kind of thing. Then you, while you walk that binary tree, you probably want to walk just the key aspects. Although I could see how those cache misses would be horrible if you're trying to make this super fast. But you don't need to carry the value of all those lookups. You just need the keys. And then once you find the right key, then and only then do you pull the value with you, if I'm understanding correctly. So I think it's a pretty good point.